Welcome back to my YouTube channel. So today's question is the mage. Sorry about I was not there for a few days. So I'm back with the graph challenge. So until now I've done 3 videos on graph challenge, and there are various videos coming up like on graphs. So till now we have understood the basics of graph, that is BFS and DFS. For the first video, the question number of distinct island make your clear understanding about DFS, and for second video, that is rotten oranges, you can see the difference between BFS and DFS. And for the third video, that is Pacific Atlantic flow, is a pretty good example of BFS. So let's go for DFS this time. So so our question for today is the maze. So this is a pretty famous DFS problem. You can see in everywhere. Like yeah. So let's see the question. So the question is, uh, there is a ball in a maze with empty spaces and walls. The ball can go through empty spaces by rolling up, down, left, or right. As I said before in my previous video, like in every problem we have to go in a certain direction, like up, down, left, or right for this problem. So in some problem you can see there are direction of diagonal direction also, like there are 8 direction flow. So you can see the you can see the alignment of these problems, right? Like these all problems are related to each other. So this is the graph problem, right? So the problem, let's back to the problem, that is up, down, left, or right, but it won't stop rolling until hitting a wall. So this statement makes this problem DFS, because you see we have to dig deeper and deeper. You see in a number of islands, right? Like you have to go for every island until you see any other water bodies like zero in that case. And in this case, we don't have to stop until we hit the ball. We don't have to we don't have to go level by level. We have to go deep into our path. That is, we won't have to stop until hitting a ball. So this is the DFS problem. This statement makes this question a DFS problem. If this statement is not there, then it become a BFS problem. Like we can go level by level and reach our destination. So let's back to our problem. That is, when the ball stops, it could choose next direction. Okay, the direction are up, down, left, or right. So given ball, start position, the destination, and the maze. Determine whether ball could stop at the destination or not. The maze is represented by a binary 2D array. 1 means the wall, 0 means the space. So you can see the similarity between number of islands and this problem. Like for number of islands, we have to go for every island till we find a water body. And for this problem, we have to go until we reach the destination, until we hit the ball. So this makes this problem a DFS one. Like you see, let's see the example here. So starting coordinate is 0, 4. So this is the starting coordinate 0, 1, 2, 3, 4. So this is our starting coordinate, right? And our destination coordinate is 4 4. So 0 1 2 3 4 4 4. So this is our destination coordinate. So let's see this example, right? So for this we have to start now. Okay, so we have a condition. We have to go. We don't have to stop until we hit the hit a wall, and we have 4 direction to go. So for first direction, we can go here. So now, so we have to check for visited nodes also, because there will be a possibility that we can revisit the node. So we have to check our what current vertices to 1, so that we can't visit again. So we have to go, this is 0. Now we have to go up, left and down. Okay, so we have to go here and here. So this is 1. Now this becomes 1, and suppose we are here, so we can go here. Okay, and you can say that all of the borders are walls. So we hit the wall here now by this. Then we hit the ball here, right? Like you are getting it, right? So now we go to this direction. So now we are here. So we can go to either this position or this position or this position or this direction. So let's say we go down there. So now not down, we hit the wall now, and eventually you can see this leads to this one, that is our destination. So in this way we reach our start to destination. You see right, like how we can use DFS for this. Now we see a problem, this example. Okay, so first we have to 0 4 and 3 2. Okay, so 3 2, where is 3 2? 0 1 2 3, 3 and 2. So this is our destination, right? And this is our start node. So we can let's start to this, let's go to this direction from this, like. Okay, so now we have visited these nodes. Okay, so now we can't go anywhere, like. Okay, we have nowhere to go, so this is trapped. So now we have to return. Now we have another direction to go, that is this. So now we are here, so let's go down direction. Now we are here, right? Like you can see, now we are here. Now we can go to this direction, and now we are here. Now we are here. Okay, then we can go to downward direction, and now we are here, like because this is wall, right? So we have to stop here. Now we can go here, like there is a wall, so we have to stop here. So now we are here. So from here, either we can go to this 0, or we can go to this 0, because we have a condition like it won't stop rolling until hitting a wall. So we have to we can't stop this ball in the middle of something. So this is our destination, so we can't reach our destination, so that's why the output is false. Like, you see the difference, right? Like, if suppose we have this problem and we don't have this condition, like, but this condition is not there, okay? Suppose we have not we can stop anywhere, then it become a shortest distance problem. That is a BFS method. We will talk about shortest distance method using BFS in another lecture, okay? So you get the approach, right? Like, first we have to go every direction, then until we find our destination. If we visit all the direction and we don't find any destination in our path, like in our destination, so we just have to return false. So this is this problem. Let's see the code for better understanding. For visited nodes, I can we can use set, like set we can add it to our set and it become easy to keep track of visited nodes, right? So let's see our code. So this is the direction, okay? So this is the direction vertex. So this is the direction, okay? And now we have a has path, like this is the main method, okay? So I'm declaring one visited set for keep tracking of every visited node, because there is a possibility we can revisit it our node back. So for and given this visited node and pass it to our new function, that is DFS. This is a helper function. So we can also use visited as our global declaration and use it in this function itself. But let's see in this function itself, like DFS, okay? So let's see our function DFS. If start is equal to destination, so if start is equal to destination, then we can say, okay, we find our destination, we reach our destination, then we just have to return true, okay? So if then again, if visited if we find this is a visited node, then we just have to return false, because this can be our path, okay? And then we have to insert our start vector to our visited vector, so that we can revisit that point, okay? So now we have to go in every direction, like up, down, left, or right. So now here is the vector of result, like this is the this can be our result, like okay, now this is the point. So we have to go deep, like until we reach our uh, we hit a wall. So either we can go here down, or either we can go left. So go deep. So the go deep function is like this, like this is the first direction, and this is the second direction, and we have to keep moving forward and forward until we reach any wall. Like this is a wall and any boundary can be wall. Then if we reach any wall, then we just have to return start. And for every role we have to keep this like for this, initially this is the start, then this will become a start. So new start is become this, and recursively we call go deep function for our new start, so that we can keep going on this direction. And again, this result, so if this result is equal to our destination, then we just have to return true. Okay, then also we have to go for every direction, right? So I am declaring, like, I am calling DFS for every direction, and at last we have to return true. And if we haven't found any destination or result, then we just have to return false, like there is no method that we can reach destination, right, from our start, because either this is between any walls or something like that. So you got the idea, right? Got the idea of DFS, like how we are using DFS. The main point of this problem is you have to keep grinding, like how DFS is working here, how DFS is working on its definition, that is depth first search. So this is the only point that is becoming that making this question a DFS problem. So yeah, this is it for today. See you in next video. I'll be back and I'll try to be consistent now onwards. Thank you. Do likes, subscribe and comment. So thank you.